Now that we've decided which bark approximation we are going to use, we'll move on to do some mapping to and from the bark scale. First, we'll, for example, can choose 64 subbands in the bark scale, hence each would have about a third bark wide, and then in Python we can construct a matrix W for this mapping, again to avoid slow for loops. And in this matrix has ones at the position of each such a third bark band. And for that we use this function here, mapping to bark mat, that constructs this matrix W, which has ones for each bark subband and zeros elsewhere. And we can see that it takes as arguments the sampling frequency, the number of filters, and the number of FFT. So the number of filters can be seen as the number of subbands. We then can plot this matrix W as an image, and this is what we are doing here. And here we have this matrix W as an image, and here we have the bark subbands, and here we have the uniform subbands. Then for each such a third bark subbands, we can add the signal powers from the corresponding DFT subbands. Then we take the square root to obtain something, let's call it a voltage again. So in Python we can define this function here that will do exactly this. It will map this magnitude spectrum vector from the DFT to the bark scale, and we can see here we have the powers, and then it will return this magnitude spectrum vector from DFT to in the barks. So the mx bark is the magnitude mapped to the bark scale, and this is what is returning here. Next step is to map from bark scale back to linear. So after having computing this masking threshold in the bark scale, we need to map it back to the linear scale of our filter bank. And for that we need to distribute the corresponding power of each of our third bark bands into the corresponding filter bank bands on the linear frequency scale. And this we take the square root to obtain something like a voltage, like we've also explained before. We again can construct a matrix to do that in Python. When there is one subband in the third bark scale, it gets a factor 1. If there are two subbands, they get a factor of square root of 2, and so on. And then we use diagonal matrix multiplication for those factors. And for example, it can be a 64 by 1024 matrix. And this is what we're doing here. So we have this mapping from bark mat, and then it constructs this matrix W inverse from a matrix W for mapping back from bark to the linear domain. Again, we can take a look on how this matrix W inverse looks as an image, and this is what we're doing here. We're plotting this matrix W inverse as an image, and now here we have the uniform subbands, and here we have the bark subbands. And the function for mapping the masking threshold from bark scale to the linear scale is given here. So we can use all these functions that we've seen to map from bark to linear or back from linear to bark, depending on our purpose.